Hello everybody, welcome back to another video. Today we're going to be working on a very unique problem actually, and it might be a little similar to my previous video, and you'll see why in just a second. So right here we have the minimum of the function x to the x. So if you didn't know, let's go right into it. Let me draw the function of x to the x. It looks sort of something like this. This is a simple drawing of it. You can draw in more detail, of course, but we see that there's local minima here at some point, and we can calculate that point analytically, which is what we're going to be doing today. So let's see how we can calculate the minimum of any function using just calculus or standard techniques. All right, imagine I have a parabola drawn in red here. This point right here is essentially where the derivative changes sign. From the left to the right, the function is decreasing, which means the derivative is negative here. I'll draw in pink. At this point at this y point right here, the derivative becomes 0. And I explained this in my previous video. You guys can check that out. And then as we ascend here, from the left to right, the graph increases, and then the derivative becomes positive. So basically, anytime the derivative switches from negative to positive, we have a local minima here. And we can prove that. So let's take the derivative. And if you aren't aware what a derivative is, I can make a video on that. Just leave a comment down below. All right, so what's the derivative of x to the x? I also made a video on that, but I'll do it here again. Let's say y is equal to x to the x. Now let me take natural log on both sides. Natural log of y is equal to x natural log of x. Now we differentiate both sides. And we're going to be differentiating x to the x using implicit differentiation, which means we have to solve for dy dx. Now if we take ddx on both sides, respecting x, ddx, on the left-hand side, we have the derivative of natural log of y, which becomes 1 over y times y prime because of chain rule. And then we get here, this is just two functions multiplying, fg, which is f prime g plus g prime f, of course. So this gives us a derivative of x, which is 1, and then ln x, plus derivative of ln x, 1 over x, times x. All right, let's simplify. We have y prime is equal to y times ln x plus 1. And we said y is equal to x to the x. So we get y prime is equal to x to the x times ln x plus 1. Now, remember what I said earlier. When we're trying to find the minimum of any function, we have to see where the derivative changes sign, and specifically, we can start off by finding when the derivative is equal to 0. So now that we have the derivative of x to the x, the function we're trying to find the minimum of, we can set it equal to 0. So we say let, in mathematics, let y prime equal 0. So that means we have x to the x times ln x plus 1 is equal to 0. Now, can we divide by x to the x on both sides? This would be valid, but we have to make sure that x to the x can never be 0. Looking at the graph, this never intersects the x-axis, so we definitely know it'll never be 0. And we're not going to be talking about 0 to the 0. I can do that in a separate video, but this usually approaches 1. There are some cases where it does approach 0, but that's not really relevant. So it is indeed valid to divide by x to the x on both sides. That leaves us on the left side with ln x, or natural log of x, plus 1 is equal to 0. And now we just have to solve for x. So we get natural log of x is equal to -1, and exponentiate both sides. We have x is equal to e to the -1. Ladies and gentlemen, this turns out this is our answer. X is equal to 1 over e. This is the minimum of the function x to the x. But we can furthermore prove it using sign charts. I explained this in my previous video as well. But a sign chart just describes how the derivative and the function changes at a specific point. And what's that specific point? It's where the derivative is equal to 0. So let's quickly draw the sign chart so we can do the full analytical proof. The sign chart looks something like this, like a number line. The domain of the function ends at, if you think about it, can this function have negative numbers? Let's say -2 to the power of -2. We get 1 over -2 all squared. So it indeed can have negative numbers. It can support that. So that means our lower bound for this function isn't going to be 0. We'll keep it a negative infinity. All right, let me draw this. Negative infinity and positive infinity. All right, So our critical point that we calculated was 1 over e, which means I'm going to be drawing a little number here, 1 over e, and then as a test value to see what the derivative is equal to on the right side of 1 over e, and then on the left side, I can do any value greater than 1 over e on the right. So that would be 100, for example, and here I will just do 1 over e, I can do 0.1, because 1 over e, I believe, is 0.3 or some number like that. I can indeed calculate that right now. We get 1 over e, plugging that into my calculator. It's about, in the float form, 0.367. That's what it's equal to. So 0.1 is indeed less than that, so we can do that. Let's write y prime here. This is the proper way to make a sign, or there's many flavors of sign charts, but this is the one I prefer. Then we have y here. If we plug 0.1 into our original equation for y prime, let's go ahead and do that. Let me do 0.1 to the 0.1, and then I'm going to multiply that by the natural log of 0.1. Natural log of 0.1 plus 1. And then I indeed get a negative number, which means our derivative here is negative. And then if we plug in 100, well, what happens? We have 100 to the 100, which is a positive number. Then we have ln of 100, which is also positive. So effectively, we get positive times positive, which equals a positive number. So the derivative on the right side of 1 over e is positive. Now, what does that mean? If the derivative is negative to the left side of 1 over e, that means the function is decreasing. And then if it's positive to the right of 1 over e, that means it's increasing. And ladies and gentlemen, that means at 1 over e, this is a local minimum, if we look at it, because that even makes conceptual sense. If the function we define like this is decreasing here and then increases here, and this point which we found was 1 over e, this must be the minimum. There's no other minimum of the function. And we proved that this is the only value such that this is true. So yeah, and that value is indeed 1 over e. It always, in mathematics, e just shows up in the craziest places, and it's so satisfying. So yeah, our minimum of the function would be 1 over e. And we proved that analytically as well. Now, you can extrude this definition and even relate it with the other function we did in our previous video. If the minimum of x to the x is equal to 1 over e, and the maximum, spoiler alert, I did the proof of this in my other video, of x to the 1 over x is equal to e, that means these are just inverses. They're somewhat related, and you can see that evident in the exponent of x to the x and x to the 1 over x. Let me know if you guys enjoy this fast-paced style of a video, if you want to see more videos like this, and leave a comment down below of future math videos I should solve. Thank you guys. See ya.